Okay, so here's the problem. Consider the objective function p, which equals 8x plus 3y, subject to the constraints negative 5x plus 4y is at most 8, 7x plus 5y is at most 63, and both x and y are non-negative. So there are two parts. In part A, we want to maximize p, the objective function, using the geometric method, which we covered in the previous video. In B, we will then maximize p using the so-called simplex method, and this we'll do in our next video. So for now, let's use our geometric approach. And we know that all we need to do now is to sketch in the first quadrant of the xy plane, as both x and y are non-negative, our feasible region, and we know that the maximum value of p will occur at one of the vertices of our feasible region. So then we'll evaluate our objective function at each vertex of our feasible region, and whichever is a larger value of p will be the optimal solution. Let's start with these two equations, or I should say two inequalities. So let's just rearrange these two to make them look more familiar. Take the first one, so negative 5x plus 4y is at most 8. Let's isolate y. So add 5x on both sides, so 4y is at most positive 5x plus 8, divide by 4, y is at most 5 quarters x plus 2. Let's do the same thing for the second inequality. So 7x plus 5y is at most 63. Subtract 7x on both sides, so 5y is at most negative 7x plus 63. Divide by 5, y is at most negative 7 over 5x plus 63 over 5. So if you look, the first inequality says that y must be always at most this function of x, and the second inequality says that y must always be at most this function of x. Well, when we sketch our feasible region, we'll consider these two lines. So y equals this and y equals this. So the corresponding line, y equals 5 quarters x plus 2. The second line, y equals negative 7 over 5 x plus 63 over 5. Okay, so with these two lines, let's try and sketch our feasible region. And remember, both x and y are non-negative, so we are in the first quadrant of the xy plane. Now your sketch doesn't have to be accurate or up to scale, as long as you get the general shape of the feasible region. That's all we need. So let's look at this line first. Well, this is a line with positive slope, slightly bigger than 1, and the y-intercept, if x is 0, then y is 2. So we have a y-intercept of 2, and you can draw, again, roughly, a line with slope slightly bigger than 1. Not that it really matters, but the slope would look maybe something like this. So that's our first line. And if you think of it, the corresponding inequality was that y had to be at most this line, and so y must be below this line. So our feasible region is going to be found below this line. What about the second line? Well, now we have a line with a negative slope, and if you think of it, if x is 0, if you look at the y-intercept, if x is 0, y is 63 over 5, which is way bigger than 2, right? 5 times 12 is 60, so this is a little larger than 12, sorry. So it's way up there. Now here I'll exaggerate. So we'll have this line that would go way up here, and it would cut through the other line at some point, and it would cross the x-axis later on. So again, this is a really inaccurate picture, but it doesn't matter. Suppose it looks like this. And again, the inequality was that y had to be at most this line, so y, again you're looking at the y-axis, y must be less than this line, and so for both lines, we must be underneath them. And now we have our feasible region, right? X must be at least 0, so we're up the x-axis. Y must be at least 0, so we're to the right of, since y is positive, we're up the x-axis. Since x is positive, we are to the right of the y-axis. And so we are below both lines, while y is below both lines, and so we are under these two lines. So this is our feasible region. And now we must find the vertices of our feasible region. Well, let's start with the easiest. This is the origin, so the vertex is x equals 0, y equals 0. This is our y-intercept, so x was 0, y was 2. Let's find this vertex, which is the 0 of this line. So let's solve for it. So we set y to be equal to 0. Let's do it underneath. Or let me just do it here. Why not? It won't take up too much space. So we want the y value to be 0. Therefore, 0 equals negative 7x over 5 plus 63 over 5. Multiply across by 5. You get 0 is negative 7x plus 63. Send negative 7x on the other side. And so 7x equals 63. Divide by 7. X is 9, as 7 times 9 is 63. So we have our third vertex, x equals 9, y equals 0. And we're missing the fourth and final vertex, which is the point of intersection of our two lines. Let's equate them. We'll solve for the x and then for the y value. So 5 quarters x plus 2 must equal negative 7 over 5 x plus 63 over 5. So let's solve for x. Send the x's to the same side, the constant to the other, so we'll have 5 quarters plus 7 over 5, factoring the x from both terms, equals 63 over 5 minus 2. We can put, well, we'll do this next, both over a common denominator. So here let's cross multiply, so we'll have 25 plus 4 times 7 is 28 over 4 times 5, which is 20, times x equals, this one is simpler, 2 is 5 over 5 gives you 10 over 5, 63 minus 10 is 53, so 53 over 5. If you notice, 25 plus 28, well, it's 40 plus 13, 53. So we get 53 over 20 times x equals 53 over 5. Multiply both sides by 20. Divide both sides by 53. And you're left with x being equal to 20 over 5, which is obviously 4. And so now we have the x-coordinate of our vertex. X equals 4. Let us now find the y value. We can use either line, as this is the point of intersection of both lines. So we could plug in 4 in here or 4 in here. Well, clearly this is the simpler equation. 5 over 4 times 4 is 5, plus 4 is 7. You can verify if you plug in 4 in here. 4 times negative 7 is negative 28. Negative 28 plus 63 is 35. And 35 over 5 is 7. So now we're almost done. We have our 4 vertices. We can create a table of values, right? So let's order them, say, counterclockwise. So we have the vertex 0, 0, 9, 0, 4, 7, 0, 2. And we know that one of these vertices will yield the maximum value of p. Let's go back. The objective function was 8x plus 3y. So p equals 8x plus 3y. And let's evaluate. X is 0, y is 0. So 8, 0 plus 3, 0 is 0. 8 times 9, 72 plus 0. So we get 72. 4 times 8, 32. Plus 7 times 3, 21. 32 plus 21 is 53. And finally, 8 times 0, 0 plus 2 times 3, 6. And so the maximum value of p is pretty obvious. It is 72. And it is reached when x equals 9 and y equals 0. And that's it. So again, these constraints define the following feasible region. The maximum must occur at one of the vertices. So once we have every vertex, we evaluate the objective function at each vertex. And the larger value in our table is the maximum possible value that p can attain inside of our feasible region. And that's it. So in our next video, we will solve the same problem, but now algebraically using the so-called simplex method.